In our world, wind is king. It carries sand, dust, and clouds like a predictable conveyor belt. We map its speed, direction, and strength, and we trust those maps to explain how storms travel. Yet the Sahara throws a curveball. A green wall of dust that on some nights slides northward against the prevailing winds, as if the desert itself is moving. This isn't a trick of optics or an exaggeration. It's a real phenomenon captured by satellite images and ground stations alike. So why does something that should be simple, wind blowing dust in one direction, behave so differently? First, let's set the stage. The Sahara sits above a hot, dry plateau. During the day, the sun heats the surface, creating low pressure over the desert. Air rushes in from surrounding seas and lands, forming what meteorologists call the Saharan air layer. That layer typically moves southward, carrying dust toward the Mediterranean. It's a well-documented pattern: warm, dry air moving north, cool, moist air moving south. Now picture an overnight scene. The sun is gone, temperatures drop sharply, and the desert surface cools faster than the air above it. This cooling creates a temperature inversion, a layer of cooler air trapped beneath warmer air. In this setup, wind direction can shift dramatically over a short distance. If you're standing in the desert at night, you might feel a gentle breeze from the south. Look just a few kilometers away and you could be watching dust drift northward. But satellites show a larger scale movement, an entire wall of dust sliding several hundred kilometers overnight. How can a local inversion explain that? The answer lies in the interaction between the desert's heat engine and the Earth's rotation, specifically the Coriolis effect. During the day, the Sahara heats the air above it so intensely that it rises, creating a low-pressure zone. At night, as the surface cools, the air above starts to sink, forming a high-pressure region. The shift from rising to sinking air flips the pressure gradient. What was once a southward push becomes a northward pull. However, the Coriolis force, our planet's rotation, acts on moving air and dust alike, deflecting them to the right in the northern hemisphere. When the pressure gradient reverses, the Coriolis effect can amplify the northward motion of the dust layer, especially if the wind speed is low enough for the effect to dominate. Think of it like a gentle push from below combined with a sideways shove from the planet itself. Together, they send that green wall drifting north. So, what appears at first glance as a simple wind-driven dust movement is actually the result of competing forces: thermal inversion, pressure reversal, and planetary rotation. The desert isn't moving on its own, it's the atmosphere doing something counterintuitive when conditions align just so. And here's the kicker: these overnight shifts are not random. They happen during a narrow window each year, when the Sahara is at its hottest of the day.